Viewers like you make this program possible. Support your local PBS station.
This has got potential for a major incident.
A wildfire races toward a sleeping California town.
Right now, guys, Paradise is on effing fire.
Residents awaken to a nightmare.
I don't want to die here!
Scientists speed toward the danger zone.
Yes, that's a scan we want.
Risking it all to unlock the mysteries of fire.
It's not something that you can just observe it and figure out how it works.
Paradise is lost.
We have witnessed literally an entire community gone.
It's the worst fire in a season of worsts. But why? A history of mismanagement,
Everywhere, foresters were trying to do the same silly thing.
a warming climate,
I think we're moving into uncharted territory.
and a building boom in the forest.
We're literally putting homes in the line of fire.
The stakes and the flames grow higher.
Right now, I'm wondering if we're in a good spot.
Inside the Megafire, right now on Nova. Another sunny day in the Sierra Nevada mountains, north of Sacramento, November 8th, 2018.
Skies are clear over Northern California today, but it is going to be a very dangerous day for fire danger.
It's been more than 200 days since there was any rain worth measuring. The forest is bone dry. And now the wind season has arrived with a vengeance.
The strongest winds are expected across the Sierra, where gusts could reach 60 miles an hour.
The stage is set for disaster. Then, 85 miles north of Sacramento, in a tiny hamlet called Pulga, the wind blows a high-voltage power line off a tower near the Camp Creek. Sparks fly. In 15 minutes, the first reports of fire come in. It is 6:30 in the morning. The camp fire has just begun. When first responders arrive, the flames are already so fierce and the winds so strong, they have trouble getting close to the fire.
Eyes on the vegetation fire. It's going to be very difficult to access. Camp Creek Road is nearly inaccessible. Have about a 35 mile an hour sustained wind on it.
It's moving incredibly fast, with a speed that stuns even veteran firefighters.
This has got potential for a major incident.
By 7:30, authorities issue an evacuation order for Pulga, where the fire funnels up a canyon, picks up speed, and explodes out over the rim. The fire is now burning an acre of forest every second. Firefighters cannot fight the flames. Instead, they focus on rescuing residents.
Pulga, it's already crossing that area, headed towards the Concow area.
The fire consumes the small community of Concow and heads toward Paradise, California, where residents have just received immediate orders to evacuate.
This fire starts, and within minutes, it's hundreds of acres.
The man in charge of the state's wildfire fighting force, CAL FIRE, is Ken Pimlott. He's never seen anything like it.
Within an hour, it is in the town of Paradise.
Paradise, nestled in the woods, high in the Sierra. A close-knit community of 26,000. Many of them retirees, drawn to the charm and beauty of life in a small mountain town. But along with it comes a looming vulnerability, about to be made hellishly evident by the firestorm stampeding toward them.
Right now, guys, Paradise is on effing fire.
Just gotta get the out of Dodge. This is getting heavy.
Residents attempt to flee,
Everything's burned. Oh my God, I mean, everything.
forced to run a gauntlet through flame. There are only 4 roads that lead off the mountain, and all of them are perilous.
Come on! Just go!
chaos captured in harrowing cell phone videos.
Oh my God, there's fires everywhere. I don't want to die here. I don't want to die.
A tense escape from hell.
I'm scared.
It's Armageddon.
It's so hot. Keep going.
Holy people don't live in their cars.
Oh my God.
It's okay.
What should we do?
We gotta get out of here.
First responders race to rescue hundreds of people trapped in their homes, cars,
Be advised, on Clark Road at Skyway, there's a woman in labor. She's in a beige Honda Pilot. She's gonna be honking her horn. We have to get the traffic moving now.
even a hospital.
All patients now out of Feather River Hospital. All patients out and en route.
Go get them, boys. Be safe.
It's now 9:30. Just to the north, in the neighboring community of Magalia, George Gold would normally be up by now, but today he sleeps in.
What woke me up was the wind. We often have wind here. I thought, oh, how nice. I open the door and it's windy. I look up and it's dark. I thought, oh, it's gonna rain. I smell the smoke. I said, it's not gonna rain. I get dressed, I go outside, I look around. At that point, the street wasn't burning, but I could see fire. And I thought, oh, this is the real thing.
He's lived here for 11 years, drawn by the quiet and the beauty. It is his dream home for retirement. Now he must leave it all behind in a hurry.
Please get out of town, and as you're going out of town, please be careful.
But the roads are clogged with traffic and obstacles, downed power lines, and trees. Crews are racing to clear the way. So George decides to wait. He drives his prized convertible to a nearby parking lot, hoping it will be safe there. He records these images as the fire closes in on his community.
You know, you stand here and you just look around, and the next thing I see that the high school's on fire. And it's just going up.
Just after noon, the fire is still raging. Many of George's neighbors are gathering in another parking lot, wondering if they are safe.
I couldn't get in at 9 o'clock.
John Robertson has lived here 8 years.
Now, this is kind of spooky, so that's what I'm looking at. As you can see, that's black smoke. Our home right now is safe. If it jumps up here to South Park Circle in Andover, it's gone.
Nearby, Mike and Alice Nutt are packing whatever they can fit in their cars.
Got soda, blankets, pillow, food, my animals. Oh, my dogs. They're my babies. And I'm just scared. I am very scared. We got our cars loaded up, don't know where to go.
"6 p.m., less than 12 hours since it began, and yet so much damage, so many lives changed forever.
Oh my God, half of our town's gone.
55,000 acres burned, at least 1,000 structures destroyed. The Nutt's house, gone. And so is the Robertsons. George Gold is mesmerized by what is unfolding before his eyes, but now he knows it's time to get out. He decides to check on his house.
When I came down here, everything was still burning. So I came here, turned around, I shot a couple pictures, and I took off. But the house was already completely engulfed in fire.
There is no hope for Magalia or paradise. And the campfire keeps growing. While George is driving towards safety, meteorologist Craig Clements is headed in the opposite direction. He and his team are on an urgent mission to shed some light on how wildfires spread.
Oh, look at that, beautiful. Yes, that's the scan we want.
It's dangerous work, but the risk comes with the possibility of a big scientific payoff.
Yeah, oh, that's interesting. We're coming into some smoke here. Perfect, perfect, perfect.
They are driving a one-of-a-kind custom rig. They hope to peer into the fire in a way that no one else has before.
We need to better understand fire spread, and the meteorological data is one of the key components. And yet we never measure things on an active wildfire. We usually use a satellite, we see plumes in the radar, which is great, but we're not really seeing what's going on right here.
Plumes, the columns of smoke and gas that rise from the flames, are more than a sign of fire. They also create their own weather, and Craig suspects that they actively spread the fire. But how? To understand, he aims a sophisticated LiDAR right at the plume. LiDAR is like radar that uses a laser beam. It bounces off the smoke particulates as they are propelled by the wind in and around the plume, and returns information about speed and direction.
We've been able to slice through a plume with our LiDAR, and we've been able to measure the rotation and the wind field associated with a rotating column, and so that's pretty exciting.
The plumes at fires like these are complicated systems. As hot air rises, cooler air rushes in. It's called fire-induced wind.
We don't know how that fire-induced wind from the plume interacts with pushing the fire front. If the plume goes up, does any air or smoke come back down? And if it does come back down, can that spread the fire in different directions? It's these interactions that we call fire-atmosphere interactions, and we don't have a great handle on how they propagate fire spread.
The camp fire continues to spread without slowing down.
Cal Fire says the town of Paradise is pretty much destroyed.
48 hours after it began, it has burned more than 100,000 acres, a grim milestone. It is now officially a megafire. Eventually, 86 lives are lost. Nearly 19,000 structures destroyed in the most destructive fire in California history. It stands apart, but it is not an isolated event. 1 year earlier, the second most destructive fire, Tubbs, burned more than 5,600 structures and killed 22. Little more than 3 months before Paradise is destroyed, the Carr megafire devoured 250,000 acres and 1,000 homes in and around Redding. 8 people perished. And on the same day the campfire began, the Woolsey fire started in Los Angeles and Ventura counties. It burned 97,000 acres, killing 3. Of the 10 most destructive fires in California history, 6 occurred in the 13 months prior to the Camp Fire.
We are doing everything we can to respond and protect citizens, but fire is part of the landscape in California. This is the normal now.
And it's not just California. Across the U.S., an area larger than the state of Maryland burned in 2018.
In the last 40 years or so, the amount of forest that burns in any given year in the western United States increased by about 1,000%. That means there's about 10 times more forest burning this year than there was in a year in the 1970s or 1980s.
All over the world, wildfires are bigger, more frequent, and more destructive. In July 2018, fires killed nearly 100 in Greece. In Sweden, fires burned above the Arctic Circle in the midst of an unusual heat wave. And huge fires burned in Canada, Russia, and Australia. Why are we living in an age of megafires?
The big question is, are these giant destructive megafires we're seeing today just the way forests burn, or is this somehow a new normal that we've created by our own actions, forest management, and climate change?
Near Paradise, firefighters have more pressing questions on their minds. Like how best to stop a fire driven by fierce wind and steep terrain, a major factor in its relentless spread. Researchers are studying this at the U.S. Department of Agriculture's Missoula Fire Sciences Laboratory.
If you were going to do fire research, this is the place to do it. This entire building is devoted to fire. It's actually a pretty complex phenomenon. It's not something that you can just observe it and figure out how it works.
Forest Service scientist Mark Finney showed us how they unlock the mysteries of fire.
So this is the burn chamber right here. Everything we do in here is designed to look at how fires behave.
On this day, he and a dozen of his colleagues are preparing for a test on a large tilting burn bed of precisely cut cardboard.
What we can do is put these on the burn bed in any kind of density that we'd like to engineer whatever kind of fire we'd like, how long we want it to burn, how long the flames are, how fast it spreads.
The burn table brims with instruments that measure pressure and temperature, taking samples 500 times a second. And there are cameras everywhere. Today, they are trying to understand more about how a fire spreads uphill, as it did near Paradise.
Okay, go ahead. Line of fire, guys. Good line. Okay.
The flames are the visible sign of rapid oxidation, or fire. Fire requires dry, flammable material, or fuel, oxygen, and a heat source to create this chemical chain reaction. Wildfires add two additional elements, weather and topography, that determine how the flames will grow and spread.
The reason we're measuring this is that you can actually get fires to accelerate extremely quickly going uphill.
Unlike the humans that fight them, wildfires move much faster uphill.
When you have a slope, you can't get air in from the uphill side as easily as you can get it in from the downhill side. If the slope is sufficiently steep, all of the air is coming in from the downhill side.
With air fanning the fire exclusively on the downhill side, the flames get pushed into the slope, putting them in contact with more fuel. The tilted, climbing fire transfers a lot of heat to the trees and brush ahead of the flames, preheating and drying them, making them more combustible.
You get very, very effective heat transfer and a much faster spreading fire.
This is what happened when the Camp Fire started. The wind funneled the flames into a steep canyon, and they rapidly accelerated uphill, right toward Paradise. On the morning after Paradise is lost, the Camp Fire is still spreading. Time for firefighters to report for the daily briefing.
Engine 83. Here. 3631 Charlie. Here. Engine 25.
All right, good morning, everybody. I got 7 o'clock. We're going to go ahead and get started with the operational briefing.
Thousands of firefighters are here, and more are on the way.
Okay, up here in Creston area, the fire has progressed to the east. It's on both sides of the river, continuing to eat its way down canyon.
Good morning, everyone.
Incident meteorologist Alex Hume is worried about what lies ahead.
There's going to be a lot of shifting winds, very dry conditions. Use your lookouts, use your communication, make it a safe day.
He taps into a suite of instruments on the ground, in aircraft, and in space. Orbiting 22,000 miles above the Earth, the 2-year-old GOES-16 weather satellite captured visible and infrared images of the Camp Fire from the beginning. The big picture of a big fire, an eerily remote vantage point to utter chaos, death, and destruction.
This particular image covers a time period from about 6 a.m. in the morning
all the way until about 5 p.m. when the sun begins to go down. Within that 11 hours, we estimate it went from 0 to about 50,000 acres. And then the following 12 hours, it grew another 40,000 acres. It released just an exponential amount of energy. And that's what we're seeing here on this satellite image.
A big factor in the exponential spread of the Camp Megafire, spotting. Hot embers, also called firebrands, launched and carried by 50-mile-an-hour winds, landed as much as a mile ahead of the fire front. New spot fires started again and again, rapidly, randomly. But exactly how spotting fuels the growth of megafires is one of the big unknowns in wildfire science.
So it's still blowing northeasterly.
Craig Clements hopes his work might lead to some answers.
This is a real strong low-level jet coming down off the mountains.
Right now, wildfire prediction models are not sophisticated enough to factor in all of the complexities of the atmosphere and terrain, and they don't account for spotting at all.
We are trying to forecast how many spot fires there will be, and that's something no model right now can handle.
Better models would help right now to keep firefighters safe as they battle the Camp Fire. But for people in Paradise, there was no time for predictions.
Having gone through Paradise, words don't describe it. I mean, a lot like the road to Baghdad during the first Gulf War when vehicles were abandoned. That's literally what it looked like. And we know some people perished on those roads and what those people went through, and they really had no warning. I think this is the first time we've ever seen an entire town in California wiped off the map by a wildland fire. We have witnessed literally an entire community gone.
The megafire that wiped Paradise off the map is more than just a big wildfire. At this scale, the physics of fire changes, greatly increasing the intensity. But why? At the Missoula Fire Sciences Laboratory, mechanical engineer Sarah McAllister is seeking an answer.
When you have a really wide plume, you're not pulling in air into the plume as effectively as you are if it's a much smaller diameter.
In any fire, colder air flows in to replace hot air as it rises. Most of the time, the air can come in from almost any direction, chaotically. It's what makes flames flicker and dance. But the flames at the center of a megafire are not fed by colder air from the sides or from above. The surrounding fire and plume stand in the way. So the only source of air for these flames is at ground level. When that happens, the plume changes. Sarah McAllister conducts an experiment to simulate that restriction of air from the side using something you might find in your own home, a chimney.
We were wondering, does that restriction in air influence the burning of the fuel underneath it? The idea is that we are scaling big fire behavior into a small fire lab-based experiment and trying to understand what's different.
She douses a uniform bed of fuel, in this case wood blocks,
It smells good, doesn't it?
with isopropyl alcohol.
Burns very nicely.
In the open, the flames are about 5 feet high as the air streams in from all directions. Now watch what happens when she slides the burning wood underneath the chimney, blocking sideways airflow.
So we're looking at 15, maybe 16-foot flame heights off of the fuel bed. Quite the increase. There's a feedback. When the fires get big, all of that air that can't come into that plume has to come in on the ground, which is basically just stoking your fire.
The chimney effect created by giant plumes makes megafires grow bigger, which further fans the flames. It's a frightening feedback loop that gets even scarier when a plume becomes a fire whirl.
Fire whirls that form on your average fire, you see them for a few seconds and they're gone.
And normally they don't prompt too much concern. But the biggest ones, literally fire tornadoes, cannot be ignored. Scientists used to think they were rare, even unlikely. But as megafires become more common, that is no longer the case. 3 months before the Camp Fire, this is what happens in Redding, California. The Carr megafire spawns a deadly fire tornado that generates winds approaching 165 miles an hour. But what causes the flames to start spinning?
This here is a fire whirl generator. It's an apparatus that allows us to study how fire whirls form and the structure of the vortex that's produced inside the whirl.
Mark Finney says they begin with turbulent, strong winds that send a lopsided current of air into the flames. He demonstrates what happens next.
You'll notice at the beginning that the flames are very disorganized, but as the inflow begins to come in a swirling fashion, the flames themselves become quite organized.
The air streams in faster and faster from the bottom, fanning the flames, strengthening the whirl.
The burning rate of the fuel increases by 3 to 8 times as the whirl begins to develop.
The fire tornado in Redding develops after the wind starts blowing inland from the Pacific. When it collides with the fire, it creates powerful swirling winds. All the ingredients of an epic fire tornado are now in place.
This was ranked as a EF3, Enhanced Fujita Scale tornado. I believe this is the strongest documented fire-induced tornado.
Temperatures reach 2,700 degrees Fahrenheit, hot enough to melt steel. It lasts for 30 minutes.
We saw things like pipes wrapped around trees, flipped over cars, power lines that were broken off from 90-foot towers that were taken down. The winds to do that are extreme.
Extreme, a word redefined by megafires as they grow in size, frequency, and impact. But the destruction they create makes it easy to overlook an important point. Fire is an essential part of a natural cycle that keeps a forest healthy.
What fire does is it essentially releases nutrients, precious nutrients, into the ground so that new plants can grow and thrive. And it creates a cycle where once plants grow enough, essentially they're setting the system up for a future fire.
The concerted effort to stop that cycle of fire began more than a century ago.
The modern fire story in the U.S., wildland fire story, begins in 1910, really.
The spring of 1910 brings severe drought to the northern Rockies. In April, hot coals spewed from a chugging locomotive spark fire in western Montana. In short order, there are hundreds of small fires burning there and in Idaho. As spring becomes summer, the drought persists, the winds pick up, and the fires grow larger. 3,000 men are on the front lines trying to beat back the flames.
There was an organization, the U.S. Forest Service, barely 5 years old, that was now charged with dealing with these large fires. 1910 overwhelmed the system completely. 3.25 million acres in the northern Rockies, most of it concentrated in a 2-day period called the Big Blow-Up.
The Big Blow-Up is triggered when hurricane-force winds turn those smaller fires into several giant firestorms. They leave a path of devastation, charring an area the size of Connecticut. 78 firefighters are killed. And the history and ecology of U.S. forests would be forever changed.
The thinking was, we could have stopped these fires if we'd had more men, more telephone lines, more lookout towers. We could have caught those fires early, and there would not have been a big blow-up.
President Roosevelt's attack on the Depression began with his emergency conservation project.
During the Great Depression, Forest Service Chief Ferdinand Silcox deploys New Deal workers and money to reshape the national forests with roads, lookout towers, and phone lines. Then in 1935, he announces something called the 10 a.m. policy.
It meant that by 10 o'clock the morning following the report of the fire, you would have that fire controlled. So if you found the fire at 10 p.m. Tuesday night, you would have it controlled by 10 a.m. Wednesday morning. If you failed Wednesday morning, then you plan to have it controlled by 10 a.m. Thursday morning.
Washington gives the Forest Service the money to make the 10 a.m. policy a reality.
So you develop smoke jumpers, you develop organized crews, you put in trails. We're going to beat back the fire menace.
Over time, the American public becomes enamored with the heroic narrative of smoke jumpers and hotshots, while being fed a steady diet of public service announcements from Smokey Bear.
Remember, only you can prevent forest fires.
The message seems clear. Forest fires are the enemy, to be avoided or attacked at all costs.
All of the science, all of the officials are very keen to eliminate fire. They see no purpose to it. It's dangerous. It's a nuisance. We will find a modern alternative.
But the war on fire creates some unforeseen consequences. With the natural cycle interrupted, forests become dense with fuel for fires. So in the 1960s and 70s, the seeds of a new kind of thinking begin to take root.
It was realized in 1978 or so that we weren't going to win by suppressing fire. We were having more fires, no matter how much money we spent, no matter how much technology we threw at the fires. The 10 a.m. policy was abandoned and a new fire policy was introduced where fire was supposed to be incorporated more integrally into wildland management.
Instead of all-out war, it is a more nuanced approach. Prescribed burns encouraged. Wildfires not attacked, but managed, allowed to burn whenever and wherever possible. But in the real world, it proves much easier said than done. It's hard to find a place where the new policy isn't at odds with a building boom in the forest. In August 2018, a case in point in the Cascade Mountains, 90 miles east of Seattle. The Cougar Creek Fire is ripping through the Okanagan-Wenatchee National Forest. The area is sparsely populated, and the fire began with a lightning strike. It might seem like the perfect place to let a fire burn. But the fire has gotten very big very quickly, and it is heading toward the small communities nestled in the forest. So the man in charge really has no choice.
Morning, everybody.
He has to draw a line in the woods and stop the fire from moving beyond it.
Today's going to be a busy fire day, so I ask that mentally we be there and be ready for that.
Noel Livingston is a veteran incident commander for the U.S. Forest Service. He first started fighting fires 36 years ago.
How do we manage this fire problem that we have? Because we have a fire problem. We have landscapes that are out of sync, and we have people living in those same landscapes. The easy solution of, well, let's just let it burn, isn't realistic.
Today, nearly 100 million Americans have made the decision to live in the woods, what scientists call the wildland-urban interface.
We love these places, and yet we're living with a certain amount of risk that they will go up in flames. We're literally putting homes in the line of fire. There are hundreds of thousands of homes that have been threatened over the last several decades by wildfires, and we expect that to go up.
Every firefighter here at Cougar Creek knows the bitter irony. Their success in the short term might make the people nearby feel safe living here and encourage even more building. But it is a false sense of security. Each time they stop a fire in its tracks, fuel for the inevitable builds up. And fires are more likely to become megafires.
because we've excluded fire for the past 100 years or so, particularly in heavily wooded stands. We're getting more of a continuous high-intensity event in those types of stands.
This ups the ante for firefighters, already doing very risky work. As the fire grows in strength, Safety Officer Jennifer Raybuck is on a scouting mission near the fire line. She aims to strike a balance between saving homes and protecting firefighters' lives.
This is our primary containment line that we're walking on. The fire is off to our right. Ideally, we'd like to hold this line.
Hot embers from the wildfire, launched and carried by the wind, are flying overhead, landing in what amounts to kindling.
If you look at some of this, it's all dry and dead, and it just flakes off in your fingers. There's nothing in here that has got any sort of resistance to take. If an ember lands in here, this piece of wood is going to catch fire.
The dead, dry wood is where spot fires start, but not where they end. With the temperature high and the humidity so low, everything here is dehydrated and highly flammable.
This is what we call tree torching or even group torching. Single tree would be one, group torching would be pockets of trees. When it's torching, it starts out on the bottom, and as those flames grow, it's sending that heat up into the live part of the tree, the green part of the tree, preheating it so it's more receptive to that build up, and it reaches a certain combustion point where the entire tree will go up. And you can see the ember wash coming off of those, and you can see how far it's going over the ridge.
This is a living tree.
This is a living tree.
What goes through your mind when you see this?
Right now, I'm wondering if we're in a good spot.
The Cougar Creek fire will burn more than 42,000 acres before it stops spreading, but no structures are damaged. Another victory for the nation's wildfire fighting force. They succeed 97% of the time. A century of excluding fire has created some unhealthy, dangerous forests all over the United States. But how best to allow forests, fire, and people to coexist? Fire ecologist Sharon Hood is testing some alternatives in western Montana.
Oh, got the pith. Nice.
This 30-acre plot is part of a long-term study to see if there's a better way to manage our forests. It hasn't burned in 100 years, and it is filled with fuel for a fire. It's hard just to plow through, much less do their work.
You basically can't see through it, and when you're trying to walk through it, you're weaving through very small trees, you're stepping over a lot of logs. It's the density that strikes me.
The dead and small trees and the shrubs are the ingredients, the fuel for bigger, more intense fires. This forest is a tinderbox, a consequence of a misguided forest management philosophy.
Our ponderosa pine forest evolved with very frequent fires, on average every 7 years. So removing fire for 100 years allows all these little seedlings to get established. If fires were coming through here routinely, they would kill those seedlings, creating open conditions.
And she has the scientific proof in the plot next door, where they thinned out the trees in 2001, then started a prescribed burn in 2002.
You're looking at this open ponderosa pine forest 16 years later. The thin and burn forest is all open space. There's not a lot of fuels, and you see the larger trees.
Back in her lab in Missoula, Sharon and her team carefully slice and analyze the core samples from the thinned and burned parcel. The tree rings tell a story if you know how to read them.
Here I have a close-up of a tree core, and each light and dark band is 1 year's worth of growth. And you can see between 1990 and 2000 in this section, You've got narrow growth rings.
Narrow rings mean less growth, nature's record of how the trees were faring before the experiment began.
And then here in 2001, there was a thinning where we cut about half the trees, and then in 2002, there was a prescribed burn, and you can start seeing really fat growth rings after that.
A forest that is more open and trees that are larger and healthier. Thinning and controlled burning clearly works, but is it practical beyond an experiment?
This type of treatment that you see here is scalable. There's no one-size-fits-all, but thinning is a major tool that we have to be able to reintroduce fire in a safer way.
It isn't the answer in every forest landscape, and prescribed burning faces a lot of opposition, ironically, from the people most in harm's way, worried about changing their view or breathing the smoke.
When we put a little bit of smoke in the air under prescribed fire, sometimes it can meet a lot of resistance from the public.
There have been some prescribed burns that were supposed to be small forest treatments, and then a gust of wind came at the wrong time and turned that prescribed burn into a wildfire.
And what about the expense? Thinning and burning can cost about $1,000 an acre, and it's not a one-time fix. But compared to the cost of a megafire, maybe it's an ounce of prevention.
I think by now, people who live in the forest or near the forest recognize that there's going to be a fire now or there's going to be a fire later, and you can have it under controlled conditions when you can go away for the weekend, or you can be running for your life watching your house burn down.
Humans have created the megafire monster, but enlightened forest management alone won't stop the infernos. Because there is another factor at play, also with our fingerprint: climate change. The Camp Fire has broken records, and yet it is only one of 3 major incidents in California right now.
We've been going from fire to fire to fire, and every time we see it, it's like, that's unbelievable. That's unbelievable. I can't believe we're seeing this.
And in the land of endless summers, there is now an endless fire season.
We're in November. This is not historically when we would see fires still occurring. It would be closer to the hotter part of the summer, but they're lasting into December now. So it's a fire year. There's no fire season.
A fire year. Year after year after year. What role do rising temperatures and changing precipitation patterns play in this trend? In California, the record wildfires occur after a historic 6-year drought.
Climate change is taking a pretty bad drought and actually causing it to be on par with the biggest droughts over the last millennium.
To better understand this link between climate and fire, paleoecologist Kathy Whitlock spends a lot of time in Yellowstone National Park.
It's a nearly pristine ecosystem where we can really see these things going on.
This is Blacktail Pond. Layers of mud beneath this ancient lake bed have their own story to tell, going way back in time.
Lakes are great repositories of environmental information. Pollen grains land on the surface of the lake and they get buried in the sediment. Charcoal from fires gets carried in the air and then sinks to the bottom. And those sediments are undisturbed. And so you get a continuous record of environmental history. 1, 2, 3. Keep it straight, keep it vertical. All right, so let's pull it up. Let it drain, turn it sideways. Okay, now we're gonna extrude. Here it comes. Nice. Woo.
Using 2 types of clues, she can learn a lot about the ancient landscape.
Pollen tells us about the plants that are growing here, and the vegetation is one of our best indicators of what the climate was. So we can use the pollen record to reconstruct past climate, and then we can compare it with the charcoal record of fires to see how periods of fire relate to periods of climate change.
The sediment at Blacktail Pond allows Kathy to look back 15,000 years, when the glaciers from the last ice age retreated from this area. Back in her laboratory, Kathy slices the cores in half and begins to take a closer look.
There's a lot going on at this time period in this lake. The light-colored layers are calcium carbonate rich. They probably were deposited by algae that were producing this calcium carbonate. And when that happens, usually it happens because the lake's a little bit warmer. The dark layers, I'm seeing little blips of what look like charcoal to me. But I suspect there's going to be a lot of charcoal all the way through this core. We just have to look under a microscope to find it.
After they chemically treat and sift sediment from the core, they can clearly identify and tally the charcoal and the pollen.
I'm seeing some large pine pollens. They kind of look like Mickey Mouse hats. And some of them, like that one, is a lodgepole pine for sure.
She has documented a long relationship between fire and temperatures. Over the past 7,500 years, fire activity closely correlates with the climate. As temperatures cooled, fire activity gradually decreased. But as humans have warmed the planet in the last century, fire frequency has dramatically increased. During the warm, dry, windy summer of 1988, 800,000 acres, 1/3 of Yellowstone Park, burned. Her analysis shows it was one of the largest fire seasons here in the past 6,000 years. If current temperature trends continue, fires of that magnitude will likely be more frequent in the future.
I think we're moving into uncharted territory. We're seeing warming at rapid rates. We're seeing extreme fire events. We're seeing things that we just haven't seen in the past. And that's my big concern. Corey, do you have all the vials?
Ecologist Monica Turner has the same concern. She and her team study Yellowstone's breathtaking lodgepole pine forests.
In Yellowstone, what I do is try to understand how fires affect the forest and then how the forest recovers.
The fires here in 1988 were part of the normal 100 to 300 year burn cycle for lodgepole pines. Although the fires were big and severe, the forests of Yellowstone recovered in spectacular fashion. But in 2000 and again in 2016, new fires hit some of the same areas that burned in '88. Monica wonders if climate change is making it hard for the forest to bounce back once again.
So that's something like 104 degrees Fahrenheit.
Whoa.
Just below the surface here.
That's hot.
Too much heat, too little shade. And what happens when forests burn again so soon before there is time to recover? To find out, they systematically count and measure tree seedlings.
D8 is dead?
And they determine how far they travel.
What we are hoping to find out here is, will they germinate? Are the conditions suitable for them to grow?
In this plot, where only 16 years separate two fires, young trees are completely destroyed. Only stumps remain, and there is, on average, a 60% reduction in the number of tree seedlings. More frequent, more severe fires and warmer temperatures mean new generations of trees will have a much harder time taking root.
We are now questioning how the frequency and the severity of fires may overcome the ability of the forest to recover. If we have future fires that happen every 15 years, I don't know.
Fire may be integral to the evolution of forests, but the scale and frequency of today's megafires appear to be something new. The landscape is changing fast, a symptom of climate change that is more sudden than most.
Going into the future, I think we're going to have more fires. And if we continue to have more fires, it will gradually shift the composition of the forests. In some places, we may lose forest and get more grassland.
The campfire is still burning, but in Paradise, embers are starting to cool. George Gold, is headed through town on his way to Magalia, just to the north. He already knows his house is destroyed. But what happened to the sports car that he left a mile away in a parking lot? Finding out is his main goal today.
There's my car. I see my car. It's there. Can you believe it? My Miata is alive. Aha! She lives.
It's time to see if there's anything worth salvaging at home.
This was my neighborhood, and there's nothing left. There's no neighborhood here. There's just debris. I mean, it was gorgeous here, just gorgeous. Peaceful, quiet. Oh, my shed's there, so I can do my gardening. This is my front door, right here. Open the door. I mean, I never considered myself a materialistic person. I mean, if you went in my house, you would say, gee, you're kind of living a Spartan life, right? No fancy stuff, just basic stuff. But the stuff I had, I loved it, right? Every time I walked in the door, I thought, oh, wow, this is my house. I've made it, I'm in heaven. And I had all these toolboxes. You know, I spent 30 years gathering tools. Here we go. They may live again. Maybe. I think not. It's really hard. I don't know what to do. I don't know what to think. I've never experienced anything like this. I don't know what to think. I don't know what to do. I don't know what to feel. I don't know. I'm no youngster anymore. I don't know if I'll ever recover.